Kokotsakis flexible polyhedra, a generalization of the orthodiagonal involute type. The study of mechanisms and kinematic systems is of interest in mechanical engineering, leading to intricate mechanical systems design. There, these mechanisms usually perform their magic deep inside machines hidden from our view. Architects, designers, and artists make use of mechanisms in a different way, putting them on full display to solve complex design problems, allowing their creations to transform and adapt to the current use case or environmental changes. Unfortunately, the repertoire of mechanisms used is quite limited. This is caused by a lack of accessible design tools for complex mechanisms and the fact that few systems can be scaled to an architectural scale at reasonable cost and effort. In the past, we investigated several new systems and their applications in design. Among others, the asymmetric deformation of surfaces or complex invertible 5-bar linkages. Now we introduce an exciting generalization of the flexible Kokotsakis polyhedron, the orthodiagonal involute type with skew faces. The use of skew quadrilaterals significantly increases the design space and the possible design's expressiveness. At the same time, the mechanism is easy to realize, we believe, even at large scales. The rotational joints are simple, and the fact that neighboring axes intersect in one point is a huge advantage over, for example, thick rigid origami. We are sure that the design community will explore the large design space and find new and exciting uses for this new class of mechanisms. We evaluated our design tool and the practicality of these new skew quad mechanisms by selecting a very extreme example from the design space with a 90-degree skew quadrilateral in the center. We built a small-scale physical model of this mechanism. The model you can see here is about 180 mm wide. The model moves precisely as expected and demonstrates the expected range of motion. To ensure that the exhibited flexibility is solely the result of its geometry and not caused by some elastic deformation or play in the joints, we built our model with tight tolerances from stainless steel. The quads are made from 0.8 mm cold-rolled laser-cut stainless steel sheets. We ground a V-groove along a diagonal of each piece and created a skew quad by bending along this diagonal. The quad was stabilized by welding in a bracing element. Small stainless steel capillary tubes were cut and welded to the edges of the quads, while various jigs ensured the correct alignment of the pieces. During assembly, hardened steel pins were inserted into the joint knuckles. All tolerances are so tight that these pins are held in place just by friction, yet the whole mechanism can be moved easily and smoothly. The prototype clearly shows the expected one-parametric motion. This is demonstrated in these stop-motion videos. On the left side, you can see photos of the actual prototype. The images on the right side show renderings of the digital model. Thank you for watching our video and your interest in our work.